Welcome back to another problem. Today we will be doing a problem involving the kinematics of rigid bodies, and specifically we'll be dealing with fixed axis rotation. So let's look at the problem statement. At a certain time t, the speed of the belt, which is here in this blue color, is 2.0 meters per second, and the magnitude of the acceleration at point x, which is on the pink disk, is 125 meters per second squared. We are asked to determine the angular acceleration of the pulley and disk system, as well as the magnitude of the acceleration at point y. And then we are given some geometrical data, which I have listed here in the givens. And so let's begin. So how do we want to approach this problem? I think it's always incredibly helpful whenever you're dealing with any kind of dynamics problem to physically think about what is actually happening in your system. So if we zoom in here and we imagine that the pulley belt system is rotating in a clockwise fashion, we can see that as the blue belt moves in that direction, it's going to spin the entire system clockwise. And because we can assume that the pink disk and the green disk are physically attached to one another, due to this material constraint or structural constraint, or however you want to imagine it, this pink disk is also going to be rotating clockwise. Now, because they are connected, that consequently means that they have to have the same angular velocity and same angular acceleration. So we can write W1 is going to be equal to W2, and alpha 1 is going to be equal to alpha 2, where W and alpha are the angular velocity and accelerations respectively. And again, we can say this confidently because they are rotating about this blue rod, which is a fixed axis rotation, and they are constrained. They are physically constrained at this interface, and so we know that they are going to be rotating together. Okay. So in our problem, we are asked to determine the angular acceleration at point x and the overall acceleration at point y. So I'll pull up my little box and we will begin. So if we wish to determine the angular acceleration at point x, we need to first break up the acceleration of x into its normal and tangential components. Now, again, you can work with different coordinate systems, but I think this problem really lends itself to normal and tangential components. So using our trusty Pythagorean theorem, we're going to have the acceleration at point x is equal to the tangential acceleration at x plus the normal component of the acceleration. And again, we're just using the Pythagorean theorem, so that allows us to write that equation. And we know that due to this fixed axis rotation, and we don't have a changing radius, we can write that the angular acceleration of t, or the tangential acceleration at point x, is just going to be r2 times alpha. And likewise, from our known formulas for the normal acceleration, in general, that's just going to be the tangential velocity squared of whatever point we're looking at divided by the radius of curvature. But the radius of curvature, again, because it's not changing, it's just going to be equal to r. So we're going to have vt squared over r2. And so if we wish to simplify this down a bit, we have ax squared, sorry about that blue box, is going to be equal to, we have r2 alpha squared plus vt squared all over r2, and then that entire quantity is squared. So if we look at what we have, we know ax, we know r2, we don't know alpha just yet. That's what we're trying to find, so that's our unknown. We do know the tangential velocity, and we'll explain that here in a second. And then we know r2. So, let's think about this real quick. So, how do we want to get our tangential velocity? As I said before, we have this material constraint and or like physical constraint of the two pulley systems. And so if we think about it and we know that the angular velocity of the smaller pulley is going to be equal to the angular velocity of the bigger pulley, and likewise with the acceleration, we can try and derive some equation to get the angular velocity, right? So what do we know so far? Let me zoom out a bit. Okay, so our goal is to determine the angular velocity. So we are given a velocity value, right? Because we have a constant radius in this problem, we know that we can write that the tangential velocity at some point along the pulley is just going to be equal to the radius of the pulley times its angular velocity. Now we are given Vz, which is a point on that pulley. So we know Vz, and then we are given the radius of the smaller pulley. So that's just going to be R1. And then we can just solve for W. So W, or the radial velocity, excuse me, the angular velocity is just going to be Vz over R1. And if you plug that in, you'll see that that comes out to being 25 radians per second. All right, let's box that guy up, and we will move along. And so let's simplify this equation right here. So we know that AN is just VT squared over R, but we just said that VT is equal to R times omega, so we can just square that term, and so that allows us to write that the normal acceleration of an arbitrary point is just going to be equal to R omega squared. Okay, so I'm going to get rid of that box. So now we can write that AX squared is going to be equal to R2 alpha, that entire quantity squared, plus R omega squared is that right? Oh yeah, squared. And that entire quantity is going to be squared. Okay? And you can see that these r's are just going to cancel out. So I'll just rewrite that again. Okay. So now if we just rewrite our equation, solving for alpha, we're going to take ax squared. We're going to subtract that term on the right. Don't forget to square it. We're going to be dividing by R2 squared, so everyone sees where I'm getting that from. We're just distributing the square. And then the big square root. And if you solve for that, we will get the angular acceleration. Recall that we're solving for point x. It's just going to be equal to approximately 345.8 radians per second squared. All right, great. That wasn't too bad. And again, let's just summarize what we did here. We recognized that the angular acceleration had to be equal between the small pulley and the big pulley. Likewise with the angular acceleration. Doing so allowed us to derive an equation to calculate omega, and that was because we were given the velocity here, and we had that constant radius from R1. Doing so, we were able to simplify our acceleration equation back, and then rewrite our equation to nicely solve for alpha, and then we did so. Okay, so what's our next part of the problem? We want to determine the absolute acceleration at point y. So we can do something very similar. Let me zoom out real quick. I'll move my box down, and then we will continue. I'm still trying to figure out how to best show that, but I'll just zoom in here, and hopefully that works. But let me know in the comments if you think that displays is if you would still like to see the picture as I'm working, and then I can try and figure out something. But yeah, so anyway, without getting too sidetracked, we have the acceleration at point y squared is going to be equal to the tangential acceleration at point y squared plus an squared, just as we had before. Recall that we are looking to solve for ay, so we'll leave that alone. Ay squared is just going to be equal to r1 omega squared squared. Recall that we just solved for that nifty expression here. Oh, I keep doing that, don't I? I keep switching the the tangential and normal acceleration equations. This is just going to be equal to r1 alpha squared plus r1 omega squared squared. Okay? Now again, how are we going to get alpha? So if you notice from before, like we said, they're going to be constrained. The small pulley or the small disk and the big disk have to have the same angular acceleration. And that is because they are constrained to rotate about the same fixed axis. And so this alpha term here is just going to be what we just calculated. So if we just take the square root of this entire term, we know r1, that's given to us in the problem. We just calculated alpha, and we calculated omega, because again, they have to have the same value between the small disk and the big disk, as we said here. And so if you just take the square root, you will get that ay is about equal to 78.49 meters per second squared. And that's our problem. So again, let's just summarize. I can't emphasize it enough. When you're working with these problems, physically think about what is happening. We have this belt being pulled to the right that causes the entire system to spin clockwise about that fixed blue axis. And because the pink pulley and the pink disk and the green disk are constrained, that is, they are physically interfacing with one another, they have to have the same angular velocity and acceleration. And by recognizing that key idea, we are able to more or less just plug and chug with our given equations for rigid bodies. So I hope this was helpful. Let me know in the comments what kind of new problems you'd like to see, and I will see you next time. Thank you.